Hello students, today we are going to discuss the first module of our curriculum, that is discrete time signal and system. It is the unit 1 of your curriculum, and today in this lecture I am going to start this. Okay, so what is the objective of this unit? In this objective, you are going to understand what is sampling of a continuous signal, why we do sampling in discrete signal processing, what is actually discrete signal, and how we reconstruct the signal. What is signal reconstruct, how we reconstruct the signal, if we do sampling, whether we should follow some rule or not. These are the things you are going to understand in this unit. Okay, so let's start with the term sampling. You know what is the meaning of sampling? Suppose in a unit of a bottle making plant, if all the bottles are proper or not, for that a manual checking is done. How? The checker or the manager sort of person engaged for that work, he used to take random samples of the bottles and check whether they are proper or not. So you can understand what is sampling. That sampling sort of thing we also do in our signal processing application. Now we do this sampling in a continuous signal. So you know what is signal? Signal is basically a information with respect to time. That is, the magnitude of the signal, the information may vary with respect to time, but what is it actually what is the magnitude we get? That is actually the signal for us. So here I have shown you this is a signal which is continuous with respect to time. That means each and every time the signal is having its unique magnitude, whatever is the value, it is always present with respect to time. Now this signal, this is a continuous signal. So this is a continuous signal. Now if I put a switch like this is nothing but a switch. Okay, so if I put a switch like this, now this switch is open now. So if I want to transmit the signal from this side to that side, I cannot transmit. The information or the signal will not pass because the switch is open. Whereas if I make the switch close, the signal will go in the other side. So if I put the switch and if I perform the making and breaking operation, that is, one time I am closing the switch and another after certain moment I am opening the switch, and I am doing this action periodically, making and breaking, then what will going to happen? So when I am opening the switch, with respect to time, no information is actually transmitted at the other end. So at that time, no signal is present. Okay, but when I am closing the switch, at that duration, certain amount of signal is going. So what is going at that time? The magnitude of the signal is actually passed through this switch in the other side. So suppose here initially the switch was closed. So initially this point I am getting the information 0 over here. After that I am opening the switch. So no information is passing on. So after t seconds, suppose after t second, I left the switch open for t second. After t second, then I put the switch again close. So after t second, suppose this is after t second, it is appearing. So this is the information. This magnitude of information at t second will be appear here. Okay, so these information will appear here. Okay, then again I am make it off, that is I am opening the switch, and I am make this opening, I am doing the opening, I am remaining the switch open for t seconds. So for if another t second, no signal is coming on the other side. Okay, so another t second, that is the second t, that is 2t times from with respect to 0, it is 2t. Okay, so this is t, this is t. So this, after this t, I momentarily, for a momentary time, I am making the switch close. Clear? So when I am doing the close, suppose this is the time I am getting these value over here. Okay, so suppose this is these value I am getting when I am doing it close, right? Again I am opening it for again t second. Okay, then I am momentarily closing it. Suppose I am getting the next thing next here. So this is basically the information at 3t is here. So now what I am getting, initially in the left hand side of the switch, it was a continuous thing, the signal was continuous. Now I am breaking, I am sometimes I am make the I couldn't able to pass the switch, I couldn't making to allow the signal to pass for certain time. So what I am doing, actually I am breaking the times, I am cutting off certain times. So I am getting certain sampled value with respect to time. I am not continuous all information with respect to time, rather I am getting some random values with respect to time. Okay, so these type of, here I have tried to show you that thing, that means it has been sampled. So this phenomena is called sampling. Okay, and what I have done, this t, after t, that as I have told you, the switch opens for t time and the switch closes momentarily. That means the momentarily, as why I have done it momentarily, because so that I can get the pulse width of the signal very small, tending to 0. The pulse width of the signal, to make the pulse width of the signal tending to 0, I have taken the switch is closing for momentary time. Okay, so these type of operation, it is, we are performing this sequentially or periodically, and this is known as uniform sampling. Non-uniform sampling is also there, but we generally use uniform sampling in case of digital signal processing. We don't do random sampling here. Generally we use uniform sampling. Okay, so here in uniform sampling we are getting that the off time, the periodicity of the switch on off is, we are taking it as 2. So time period of this switch, this device, is actually 2. What is t? This t is basically the off duration, when the duration for which I am cutting off the signal from the system. Okay, so now what I am getting certain sequences. Now it is not the continuous thing, I am getting some sequences over here, and this phenomena is known as sampling. So in sampling, what we do, we actually convert the continuous signal into, this is not a digital signal, this is basically a discrete signal. So what is actually discrete signal? What is actually discrete signal? Discrete signal is discrete with respect to time, but it is continuous with respect to amplitude. Here you can get that what is the amplitude in the actual signal was reflected over here, but what we are doing, we are actually making the time discontinuous. Okay, so this is discrete signal. So discrete signal is discrete in time. Okay, because now time is not at all continuous. Rather than time, we will get them in sequence. We will get these are basically, we can represent them in form of sequences, like 0, it is the first sequence, first sample, 0 or zeroth sample, then it is the first sample, so it is the first sequence of sample. This is the second sample, this is the third sample, this is the fourth sample. So now it is not time, it is n. What is n? N is actually sequence of discrete signal. It is representing the number of sequences. Okay, so in discrete signal, we are actually making the time discrete, but the magnitudes, what is the magnitude at that particular time when it is passing on, what is the magnitude was there, it is coming to us. So in the magnitude, it is the same thing you are getting at that particular time, but we are actually obstructing the continuous flow of time. Okay, so this is basically the discrete signal. Now this type of we can able to represent the discrete signal in many forms. Now what I have drawn here, it is called graphical representation, where the x-axis will give you the sequence. It will be n. It will be n. So the n is the, what is n? N is nothing but sequences. Okay, so what is sequences? N is starting from 0, 1, 2, 3, 4, any number of sequences can be n. It will be obviously a whole number. Clear? Next is, we can do this a type of representation is graphical representation. Another type of is called functional, another is tabular, another is sequences. So just let us know what are the other type of, like what is we know what is graphical, so let us know what is functional. Okay, so what is functional? How we represent the function, do the functional representation. So functional representation of discrete signal. So suppose if I write, this is we generally express, we can put a square bracket, or we can put a parenthesis also. So suppose I am writing that for fn equal to 1, for n equal to -1, equal to 0, for n equal to 0, equal to 2, for n equal to 1, equal to -1, for n equal to 2. In this way, if I write it in this way, it will be known as functional representation. Okay, now what is tabular representation? Tabular representation. So tabular representation, you can understand, it will be in form of table. So how we will give it? Suppose there will be n. Okay, so what are the values of n? I am representing this one only. So the n is value is from suppose from -1, the value of n, the sequence is from -1, then 0, then 1, then 2. So what will be the value of the functions? So the functions will be at -1 it is 1, at 0 it is 0, at +1 it is 2, and at +2 it is -1. So if in this way it is represented, it is known as tabular representation. And the last one is very interesting, and we will use this mostly, that is called sequence representation. It is very easy to use. So now I am showing you the sequence representation. So what is sequence? It will be written in a sequence like Fn will be, we will use a curly braces over here. So it will start it from n equal to -1. So what is the magnitude? We will write only the magnitudes of Fn. Okay. So it will be starting from 1, then 0, then 2, then -1. Now how can I understand which is which comes under which sequence? So for that there is a very clever approach, that is, if you put we have to put a arrow sign under the 0th sequence. So which is the 0th sequence? It is the 0. So it will be this type of arrow will be provided. That means this is the representation of 0th sequence. So you can understand that before it will be -1 and after it will be +1. So this is called sequence representation. Okay. Now we are going to start a new thing, that is unit step sequence. We know all what is a unit step function or how a unit step signal look like. We know it will be like this. This is a continuous signal. Now if I make the sampling unit time ahead, so I can get after 0 I will get the sample value at 1. After that I will get the next sample value at 2. So this is basically, it is giving me, I should write this for ft was ut. So this ut is now converted after going through this switch or sampler, we can call it a sampler. So after flowing through this sampler, it is actually now converted into sequences of unit value. So this is my this is the signal, this is the unit sequence, unit step sequence. So how can I write the expression of unit step sequence? Obviously I can write un will be equal to 1 for n greater than equal to 0. So the sequence, when the sequence is 0 or positive sequence, it will be 1. It will be 0. It will be 0 otherwise. Right? So we know, just like what we get in continuous domain, it will be just like, but it will be represented in form of sequence only. Next is what we get. This is actually my delayed step function. So function, it will be ut minus 3. So this is the signal ut minus 3. Now if this goes through the sampler, what it will look like? It will be like this. The sampling will start from 3, then it will be 5, then sorry, it will be 3, and then it will be, so unit sampling, if it is the sampler is unit time delay with the unit time duration, so it will be 4, then it will be 5. In this way it will go. Okay, so naturally we can able to write the expression of this also here. This value, that means this function means un minus 3 will be 1 for n greater than equal to 3. It will be, so un, this function n minus 3, it will be 1 for n greater than equal to 3, and it will be 0 otherwise. Okay, so this is basically the delayed step function. We can get the similar type of approach in unit step sequence, delayed step sequence, only the time will be converted into sequences. Now from here, if I told you that I have a signal like this. My UN, this is my UN. Okay. Now, and I have a UN minus 1. That means this is 0. This is 1, this is 2. I have, this is 0. Clear? So, it will be 1, 2, 3. So, this is basically my delayed response U of n minus 1. So, if I just subtract these two, if I subtract UN from UN minus 1, what I can get? This value at 0, the value is 1. Here the value is 0. So I will get a 1 over here. Right? At 0 I will get 1. Next here, this is 1. This is also 1. So they will cancel out. This is 1 as well as this is 1. So they will cancel out. This and this also cancel out. So each and every one will be cancel out. Only I will get this function with respect to time if I subtract a unit sample step sequence and a unit delayed step sequence. So the thing I am getting a unit value of a signal at 0 only. We will call it a sample sequence. Okay, and we will express it with this symbol delta. So we will express delta n. Delta n, it is just like impulse, or we will call it a unit sample sequence. So this is actually only, so delta n is only, we can obtain delta n equal to 1 only at n equal to 0. It will be 0 otherwise. We know it is basically the definition, matches the definition of unit impulse function, right? Now how we will get? We will get this un minus 1, and we are getting basically delta n. So this function delta n, now in this way we can represent the delta n. This will be called as difference equation. This is very important. In continuous domain we know that there is a relation between step and impulse. What is that? That if you actually, the integration gives us the from impulse you can get the step, as well as from the step you can get the ramp. With the help of, there actually one signal is actually associated with either with integration or a differentiation. So when we express a differential signal, we call it a differential equation. When we express signals in form of differential equation, but here in discrete domain we cannot express it in form of differential, rather we will express it in form of difference. As it is not continuous, we will going to get it in form of difference. So this delta has a property of un minus 1. So this will be expressed as a difference equation. So if I want to write the generalized value of delta n minus k, I can definitely write it as u of n minus k minus u of n minus k minus 1 will give us the delta n minus k, this expression. Okay, so in this way we can able to get the unit sample sequence from the difference equation of unit step signals. Now it is very important that we will obviously discuss the properties of delta. Delta is a very important thing. So delta function has certain properties. We will discuss it afterwards. Now from what we have learned in these two slides, can you tell me what we will get if we take two ramp? Here you can able to understand that the ramp function will be just like, we know that in in continuous domain the ramp is actually equal to t. We know the expression is t for t greater than equal to 0. Here as we substitute this t, the continuous value, with the sequences, how we actually substituting this t, because we are actually, if you know what we are actually doing in continuous with when there is we are doing the sampling, what we are doing, we are replacing the t with respect to n t, where n are the sequences and t are the time period when the sampler is off. So if it is 0, this means it will be definitely t, then it will be 2t, then it will be 3t, then it will be 4t. So in this way it will be 8t, but as t is the common thing, and if we have a value of t, obviously for a regular system, a practical system, we cannot write t, rather this value, this t is having certain time value. Okay, so naturally it is basically the sequences what we can express. We can express them in form of sequences because t is nothing but a constant value. So naturally we express them in terms of n. Okay, that's why we are writing that the ramp is equal to, not writing nt, we are writing the value of sequences n. Okay, so in this way, so when it is the sequence is 0, that means the first thing, the first value will be 0. When the sequence is 1, that means this value will be 1. If the sequence is 2, that means this magnitude will be 2. Similarly, when the sequence is 4, the magnitude will be 4. When the sequence is 8, the magnitude will be 8. In this way, we are going to make the unit ramp sequence. Now, if I want to get this Rn minus Rn minus 1 excuse me, what shall I get? What shall I get? If I do this, what shall I get? So if I do this Rn and Rn minus 1, that means this is my Rn. So Rn minus 1 will be starting from here. So Rn minus 1. So what it will be? In Rn minus 1, the value must be 0. Okay. At Rn minus 1, the value will be 0. Then for that means it will be 0 when it will be 0 at t. At 2t, it will be 1. At 3t, it will be 2. So in this way, if you just subtract, what you are going to get? Okay, let me draw it for your clear understanding. Let me draw it with a new color. First, I am drawing Rn. So what we have discussed, as per that Rn, if I draw Rn, this will be n. So when n equal to 0, this value will be 0. When n equal to 1, this value will be 1. When n equal to 2, this value will be 2. When n equal to 3, this value will be 3. When n equal to 4, this value will be 4. In this way, it will go up. Okay. Similarly, if I want to draw Rn minus 1, if I draw Rn minus 1, so it will, what is basically, it is shifted by 1. So, whole thing will be shifted. So, 0 will not appear at 0, rather it will be appear at 1 because it will be shifted in the right hand side. Okay, so that means as per that it will start from here. So, what is ramp Rn minus 1? It will be equal to n for n greater than equal to 1. Okay, so at 0 it will be 0, it will be greater than equal to it will be greater than equal to 1. Okay. So here you can understand that ramp is basically, we cannot write when a ramp is shifted, we cannot write only this part. Why? Because we know it will be a straight line which is not passing through origin. So that means it should have an intersection. So here there will come another amount which is a constant part, and this constant part will obviously come with a shifted ramp. It doesn't come with any other signals in continuous as well as in discrete, but in ramp you cannot write it in this way, but you have to, what you have to write, you have to write it. So these type of signal writing in case of ramp is not valid. So you cannot write it in this form. Rather you will write it is having a expression like ramp n minus 1, or ramp, a certain ramp should have a y is equal to mx plus c sort of expression. Okay, so if you go through that, you will find that these will we will start from, we will not going in this part, we are only starting from the where the ramp is cutting the 0 value. So here we are getting, if we shift this ramp in the right hand side, this will be 1 shifted in the right hand side, so it will be 0 over here. Next we will get that this second value will come to the next part, that is it was 1. So this value is basically 1. It will come, this magnitude 1 will come to the second sequence. Naturally next magnitude, that is second magnitude, will come to the third sequence. Similarly the third magnitude will come to the fourth sequence. So in this way it will go. Now what I am asking you, that if you take this Rn minus R minus n, what you are going to find? You are getting that here you are getting a 0. What you are getting? You are getting a 0 over here. Okay, so you are getting a 0 over here. So the new signal will be like, this is 0, this is 0, so you are getting a 0 over here. Then you are getting, this is 0 but this is 1, so you are getting a 1 over here, right? Then this is 2 but this is 1, so you are getting another 1 over here. again you are getting another one over here. So in this way, all of the way you are getting only ones. So only the first sequence is 0 and the all of the sequences you are getting nothing but 1. So what is this? This is nothing but u of n minus 1. So if you take the difference equation, if you take the difference between a general ramp and a shifted ramp by 1 unit, you will get a step signal, a shifted step signal by 1 unit. Okay, so you can also write it in this way, that r n plus 1 minus r n, this will also give you a step signal, but this will be like this. So in this way, depending upon if you want to generate a step from a ramp, you can able to understand that depending upon the values of ramp, you can generate the step of your requirement. Okay, so in this way we can get the difference equation. From the difference equation of two ramp, we then get the unit step. Next, this is the very important part, and it will you need this very much. So just try to understand what I am trying to say here. This is a continuous signal xt. I am taking a black box over here. So what I want to do, how actually I want, we know physically how the sampling is happening. But if when you are going to write the mathematical expression of sampling with a continuous signal, what is the mathematical phenomena happening, so that you are getting a discrete sequence from a continuous time signal, that we are going to understand now. That is, we are going to get the expression, the mathematical expression of discrete signals. Now what I have told here, there is a black box. In the black box, two signals are acting. One is a continuous signal, another one is sum of shifted impulses. So what is sum of shifted impulses? Try to understand. Suppose I am taking a impulse signals. You know what is impulse? That is sample sequence. Okay, so sample sequence, I am taking it like this, delta n. Okay, so this is delta n at n equal to 0. So this is my delta n. Next, I am taking another delta, but it is shifted by 1 unit. So if it is shifted by 1 unit, how can I take it? Suppose this is my 0, but my signal is shifted by 1 unit. That is, this is where it is. It is actually the unit, the value is 1. This is actually at n minus 1. Okay. Now another signal which is shifted by 2 unit from the original signal. So if it is 0, this is 1, this is 2. So I am getting another delta which is shifted by 2 unit. In this way, I am taking so many deltas and I am sum all of them. I am add all of them up. Okay. So in this way, I am adding all the deltas. So this is 0. So 1, 2, 3. So here my delta is there. And I am adding all the delta functions, right? So what is going to happen now? So first, it is a continuous signal. Suppose this type of signal it is. So continuous signal xt. These two will be in the black box. Suppose they are multiplied. So at x equal to t, when the value of x is equal to 0, okay, at that time I am getting a 1 magnitude function is acting with it. So what I am getting? I am getting that this signal will be come to the other end of the sampler. So I am getting that signal. So if I write that signal, that is, it is actually on the 0th sequence. At the 0th time, actually this is acting. This is acting. So I am taking x0 and along with it a delta. What is the value of n over here? N is 0, so it is basically a delta 0 function. So delta, what is delta? What is n here? It is n means n is equal to 0. So this delta n function is actually acting on it. Now what happens to this function, this xt? Nothing is acting with. From here nothing is coming, 0 is coming. So as it is multiplied, naturally this part is not here. Rather, after 1, when x we are getting the sequence is equal to 1, okay, or equal to t, whatever you say, the t equal to nt. What is n? N is basically 1. Okay, at that time we are getting that another 1 is coming. So whatever be the signal was present at x equal to capital T, whatever be the signal was present equal to x equal to capital T is coming to my side, this side, right hand side. So what is the signal coming? I am getting that x, I am writing, not writing the t, only the sequence I am writing. So x1 is coming and this signal delta n minus 1 is multiplied with that particular value. So this is also coming. Next, just after that part, after just t, nothing is coming. So I don't know, nothing is coming here. So 0 is coming. So nothing is coming from here. Only where it is coming? It is coming when the sequence of xt equal to 2t. xt equal to 2 x t equal, sorry, t equal to, sorry, this will be t. This will be t. When t equal to 2t, at that time we are getting that a unit function 1 is coming. So that is multiplied with the signal at only 2t. So if I write it, how can I write? I will write only the sequence. So it will be only 2. I am omitting the t and it will be delta n minus 2. So in this way, basically if I add it all up, I am getting that this signal is actually coming in the right hand side. Okay, so if this is the signal and if I want to write it in a generalized way, what I can write? X is present there. If I take a summation sign, if I take a summation sign like this, and if I want to write it in form of, this is n, so this is 1, this is 2, so I have to take another value. So let's take it k. Okay, so if it is starting from k equal to 0, so k will be equal to 0, so this will be my k. xk, x0, x1, x2, this will be my k. So what will be the value of here? What will be the, it will be delta n minus k. Understand? And if I go, it will be go up to infinity. So I can take the value of k up to infinity. So you can find that it is becoming the expression of discrete signal, mathematical expression of discrete signal after sampling. So this is very important. When you are actually making a continuous signal into discrete, what you are doing? You are actually multiplying. What you are doing? You are multiplying the input with shifted, sum of shifted impulses. Okay, you are multiplying the input with sum of shifted impulses, and in this way the expression will be expressed. This is the mathematical expression for any discrete signal. Understand? Okay, so this is today's lecture is up to this. Thank you.